Right now, a fleet of NASA spacecraft are studying an object that was never supposed to be here. It came from somewhere else, somewhere older. And when the James Webb Space Telescope finally decoded its chemistry, scientists stared at the numbers in disbelief. Not because the data was wrong, because it was right. And what it revealed was so far outside any prediction that the lead researcher at NASA's Goddard Space Flight Center stood in front of his colleagues and described what they were looking at as a sample from the ancient galaxy. A relic from a time so distant that the stars which built this object have not existed for billions of years. The object is 3I Atlas, the third interstellar visitor ever confirmed to pass through our solar system. And what James Webb found, frozen inside it, locked in chemistry that has not changed since before our sun was born, has rewritten what scientists thought they understood about the material that drifts between the stars. Before that discovery, 3I Atlas was already unusual. From the moment it was detected on July 1st, 2025 by the Atlas Survey telescope in Chile, the numbers coming back from it did not behave the way interstellar objects were supposed to behave. It was moving at speeds in excess of 130,000 miles per hour in an unusually flat trajectory, inclined only 4.89 degrees from the ecliptic plane. Its orbit was hyperbolic with an eccentricity of 6.14, so far beyond the threshold for an unbound object that there was no question where it had come from. This was not a solar system comet that had wandered off course. It was a traveler from another star, arriving with chemistry and physics that nothing in our catalog had prepared us for. For months, observatories on the ground and instruments in orbit tracked it as it moved steadily closer to the sun. Its light flickered in unusual patterns. Spectrometers detected enormous amounts of carbon dioxide pouring off the surface, far more than any comet in our solar system had ever produced relative to its water content. The ratio was so extreme that every model scientists tried to apply to it came back with numbers that did not fit. The carbon dioxide abundance was accompanied by traces of water, carbon monoxide, sulfur compounds, water ice, and an abundance of dust. It was as if the object had preserved chemistry from a colder, darker environment that predated our sun, one where the normal balance of ices and volatiles followed rules that nothing in our solar system had written. Still, most scientists wrote off the unusual chemistry as a quirk of formation. Different star system, different starting conditions, slightly different proportions. Interesting, but not yet alarming. The deeper truth was still hidden inside the ice, waiting for the right instrument to find it. Then came the final approach. On October 29th, 2025, 3I Atlas passed its closest point to the Sun at a distance roughly equivalent to Mars's orbital radius. Ancient ice that had never been warm before, frozen since before Earth existed, began to sublimate for the first time. Whatever had been locked in the interior layers for billions of years was now venting into space, and James Webb was watching. Webb sniffed methane from the interstellar comet in mid and late December, roughly 2 months after perihelion. The amount of methane relative to water was surprisingly high compared to other solar system comets. Methane is highly volatile. It sublimates easily under even faint warmth. The fact that it was still being detected months after perihelion, still pouring off the surface in quantities that dwarfed anything seen in a solar system comet, told scientists something specific and alarming. This object had not been processed by heat in a very long time. Its volatile reserves were enormous, untouched, preserved at near absolute zero temperatures, for a duration that the numbers were starting to suggest was almost incomprehensible. Then the NI-RSPEC data arrived. The near-infrared spectrograph on James Webb, analyzing the December observations and the months that followed, returned 2 measurements that changed the conversation completely. Carbon isotopes and hydrogen isotopes. 2 chemical fingerprints, 2 numbers, and both of them pointed to the same conclusion. The NI-RSPEC data revealed only small amounts of carbon-13, as opposed to its lighter counterpart carbon-12. Since carbon-13 enrichment is known to occur in warmer, denser stellar environments, its absence in 3I Atlas suggests the comet did not form anywhere near such conditions. Carbon-13 builds up when carbon chemistry happens in warm, dense, star-forming regions. Our own solar system went through exactly that kind of environment when it formed. The comets born around our sun carry the carbon-13 signature of that warm, dense beginning. 3I Atlas carried almost none. Whatever environment produced it was cold, remote, far from any stellar nursery, a place where carbon chemistry ran quietly in the dark with none of the warmth that stamps a formation fingerprint into a comet's ice. And then the hydrogen. Scientists found 30 times more heavy water in the interstellar comet compared to the typical solar system comet, and more than 40 times the heavy water found in Earth's oceans. Heavy water is water where ordinary hydrogen has been replaced by deuterium, a heavier form of hydrogen with an extra neutron in its nucleus. The ratio of deuterium to ordinary hydrogen in a body of ice encodes the temperature during formation. Cold environments far from any star produce high deuterium ratios. Warm environments close to a star, over long periods, process that ratio down, converting the heavy water into ordinary water through chemical reactions driven by heat. Our solar system's comets carry deuterium ratios shaped by 4.6 billion years of thermal processing under our sun. 3I Atlas carried a deuterium ratio 30 times higher. The ice inside this object had not been significantly processed by any star's heat. It had been sitting in the dark, at temperatures near absolute zero since the moment it formed. Inside laboratories and observatory control rooms across the world, when those numbers came back, the atmosphere changed. Scientists stared at graphs and checked calibrations and ran the analysis again. The equipment was fine, the numbers were real, and what they meant was something that took several readings to fully absorb. Researchers estimated that 3I Atlas may have formed 10 to 12 billion years ago. That is nearly 3 times the age of our solar system, 10 to 12 billion years. The universe itself is only 13.8 billion years old. At the upper end of that estimate, 3I Atlas formed less than 2 billion years after the Big Bang, in the earliest era of galactic star formation, when the Milky Way was young and the stars being born inside it were nothing like the stars forming today. The object that had just passed through our inner solar system was not a contemporary visitor from a neighboring star system. It was a fossil from the early universe, a chemical archive from an era so remote that the stars which built it burned out and died billions of years before Earth formed. Martin Cordner, astrochemist at NASA's Goddard Space Flight Center and lead author of the study published in Nature in June 2026, described what that means in terms that have stayed with everyone who read them. This was a unique opportunity to study an ancient object from the distant galaxy, probably predating our sun and solar system. On the one hand, we get direct insight into that distant time and place. And on the other, we learn something about how unusual our own solar system may be. How unusual our own solar system may be. That sentence is doing more work than it first appears to do. Because what the deuterium ratio and the carbon isotope ratio together imply is not just that 3I Atlas formed somewhere unusual. They imply that the conditions which produced our solar system, the warm, dense, chemically active stellar nursery that gave us our particular mix of ices, and rocks, and eventually oceans and life, may not be the universal template. They may be the exception. Stephanie Milam of NASA Goddard said, "So far, we know of only one place in the vast cosmos where chemical ingredients led to life, our solar system, our Earth." Analysis of these interstellar objects is a major step towards learning how common, or uncommon, the conditions for the evolution of life are in the universe. Common or uncommon? That is the question 3I or Atlas has put back on the table. And the direction the evidence is pointing is not the comfortable one. By the time the Nature paper was published, the window for observing 3I Atlas was already closing. The comet was moving back, out of the inner solar system, losing gas production as its surface cooled, fading in every instrument's field of view. Webb observed a sharp decline in gas production as 3I Atlas moved farther from the sun, with water showing the most pronounced drop. The sequence of shutdown, which volatile stopped venting first, and which persisted longest, gave researchers one final piece of data about the layering of ice inside the nucleus. How the object was assembled, layer by layer, across billions of years of cold accumulation, read out in the order its molecules stopped speaking. And then it was gone. Not destroyed, not captured. Just gone. Back into the interstellar medium from which it came, carrying whatever remained of its ancient ice out of the solar system at 130,000 miles per hour, heading toward a destination that will take millions of years to reach, if it ever reaches anywhere at all. A fleet of instruments had watched it go. Few, if any, comets have ever been observed by as many spacecraft as 3I Atlas. Hubble, Webb, Spherex, Maven, TESS, Parker Solar Probe, Europa Clipper, the Lucy spacecraft, Mars orbiters. Combining data from these different missions delivers powerful new insight that no single mission could provide, and the data from all of them is now sitting in an archive, still being processed, still being analyzed, still yielding results months after the object itself crossed beyond practical detection range. A comprehensive SETI search found 0 radio technosignatures. 3I Atlas was not a spacecraft. It was not a signal. It was something in some ways more extraordinary than either of those things. It was the oldest object ever directly. Sampled in the history of planetary science, a piece of the early Milky Way that the galaxy itself sent into our solar system at precisely the moment we had instruments capable of reading what was inside it. Whether that timing is coincidence or simply the predictable consequence of interstellar objects being more common than anyone had. Assumed before 2017, the result is the same. We have now held in our telescopes a sample of chemistry from a universe we will never otherwise be able to visit. A universe 10 billion years old. In a galaxy still learning how to form stars, building objects from ice and carbon in conditions nothing in our solar system has ever replicated, and it passed close enough for Webb to smell its breath. With the advent of ever more powerful telescopes, these discoveries will become much more common. The Vera Rubin Observatory, which began its 10-year legacy survey of space and time on June 30th, 2026, is expected to detect interstellar objects at rates that will make 3I Atlas look like the beginning of a long conversation rather than a singular event. The next one is already out there, crossing the distance between stars at speeds no planet could match, carrying chemistry from somewhere we have never been. And when it arrives, we will be ready. But none of the ones that come after will be 3I Atlas. None of them will be this old, or carry this specific fingerprint, or have passed through our solar system at this particular moment when this particular set of instruments existed to receive it. Humans only recently developed technologies capable of spotting interstellar objects passing through our solar system, said one of the researchers involved. That is the sentence that carries everything. We almost missed it entirely. We had a window of 7 months, and in those 7 months we read 10 billion years of history frozen in ice. The universe did not pause for us. It passed through. And we were just barely ready to listen. That readiness was not accidental. It was the product of decades of telescope development, survey network construction, instrument calibration, and the particular luck of SphereX launching in March 2025, 4 months before 3I Atlas was discovered, providing the first detailed carbon dioxide abundance measurements of any interstellar object in history. A slightly different timeline, and the chemistry would have been less complete. A slightly different trajectory, and the perihelion would have been too close or too distant for the post-perihelion observations to work. A slightly different formation environment, and the deuterium ratio might have been indistinguishable from solar system comets, and the 10 billion year age would never have been estimated. Every one of those variables landed in the right place. And what we extracted from that alignment is a sample of the universe that no mission could have traveled to collect. From an era of galactic history, no telescope could have reached back to observe directly. It came to us, 10 billion years old, carrying the fingerprint of the early Milky Way in its ice, whispering the chemistry of a universe we will never otherwise be able to touch. We were ready, barely, and it will not come this way again.